when we apply the concept of multiple reference frames, there are two cases that may arise. First, the secondary reference frame is fixed with respect to the rigid body, or in other words, omega is equal to omega bar. The other case, the secondary reference frame is not fixed with respect to the rigid body, or in other words, omega not equal to omega bar. This we had discussed in the last class. In this lecture we shall be discussing more about this one. In many cases, what happens is that you will have the primary reference frame capital XYZ, and then you will have a moving reference frame small xyz. Now the moving reference frame may be undergoing an instantaneous angular velocity omega as such for an instant of time. Now the rigid body here, the rigid body may itself have an instantaneous angular velocity t omega relative REL with respect to this moving reference frame, or in other terms, this value can be expressed in terms of omega bar with respect to the fixed reference. Okay, so the rigid body itself is having an angular velocity with respect to this moving frame small x, small y, small z. That is, the xyz frame is not embedded in this rigid body. So if I consider a point P here, now with respect to this moving reference frame, this point P will be in motion. So we will try to derive the velocity and acceleration of the point P with respect to the fixed reference frame capital X, capital Y, capital Z. So I have shown you the figure once again. You have the primary reference frame capital X, capital Y, capital Z, and the secondary reference frame small x, small y, small z. Now R is the corresponding position vector of the origin of the secondary frame with respect to the origin of the primary frame. The moving frame is undergoing an instantaneous angular velocity omega with respect to the primary frame here. The point P itself is in motion. Okay, so the rho vector here will not be fixed. Since the point P which lies within the rigid body is in motion with respect to small x, small y, and small z. So let us try to derive the equation. Now we can relate the position vectors like we did last time. R equals capital R plus rho, where R is the position vector of the point P with respect to the fixed frame capital XYZ. Now if I differentiate this, I would get dr by dt with respect to capital XYZ is equal to dr by dt with respect to capital XYZ plus d rho by dt with respect to capital XYZ. Now we already studied that dr by dt with respect to capital XYZ will become Vxyz. Dr by dt, d capital R by dt with respect to capital XYZ will become R dot. and this corresponding vector. As such, rho is not a fixed vector. Rho is not a fixed vector. If you remember, we had studied that dA by dt with respect to capital XYZ is equal to dA by dt with respect to small xyz plus omega vector cross A vector. All of these are vectors. Okay, so as such, this corresponding term d rho by dt with respect to capital XYZ will be equal to d rho by dt with respect to small xyz plus omega vector cross rho vector. All are vectors. Now d rho by dt with respect to small xyz is actually the velocity of the corresponding point P with respect to the moving frame xyz, small x, small y, small z. So this equation turns out to be in this format. So applying all these, I get the velocity of the point P with respect to the primary frame capital XYZ is equal to the velocity of the point P with respect to the moving frame small xyz plus r dot plus omega vector cross rho vector. This equation you will have to study it by heart. Now differentiating this once again, dv xyz with respect to dt relative to the primary frame capital XYZ is equal to dv with small xyz with respect to dt relative to capital XYZ plus r double dot plus d by dt of omega vector cross rho vector relative to capital XYZ. Let's look into each of these terms. Now d v x y z capital XYZ with respect to dt relative to primary frame is equal to the acceleration of the point P with respect to the primary frame capital XYZ, and d by dt omega cross rho vector with respect to the primary frame XYZ is equal to, differentiating by parts, omega vector cross d rho by dt with respect to capital XYZ plus d omega by dt cross rho. Now this we had already studied that derivative d rho by dt with respect to capital XYZ is equal to d rho by dt with respect to small xyz plus omega vector cross rho vector plus d omega by dt with respect to capital XYZ cross rho vector. It is equal to omega vector cross velocity with respect to small xyz plus omega cross rho plus omega dot cross rho vector. Now the next term here is dv xyz by dt with respect to capital XYZ. Here we know the equation dA by dt with respect to capital XYZ is equal to dA by dt with respect to small xyz plus omega vector cross A vector. So instead of a here, we are replacing a with velocity of small xyz. Okay, so as such, dv xyz with respect to dt whole with respect to xyz is equal to dv xyz by dt whole raised to small xyz plus omega vector cross vxyz vector, which in term I can write it as this corresponding dv small xyz by dt with respect to small xyz with respect to small xyz is actually the acceleration of the point P with respect to the moving frame small xyz plus omega cross v with respect to small xyz vector. So substituting all of these, okay, this and this in the above equation here, okay, we get acceleration with respect to capital xyz will be equal to a with respect to small xyz plus r double dot vector plus 2 omega vector cross v with respect to small xyz vector plus omega dot vector cross rho vector plus omega vector cross rho vector. The equation may slightly look a bit bigger, but as such you will have to remember this equation. Now if we look into the acceleration obtained, when omega is equal to omega bar, that is in the earlier case the equation was a vector with respect to capital xyz is equal to r double dot vector plus omega dot cross rho vector plus omega vector cross rho vector. If you look both of these equations, two terms has increased. One is this and the other is this. Okay. Now this corresponding term here is called the Coriolis acceleration, named after the French engineer G.C. Coriolis. That is, you have a rigid body that is rotating with respect to the moving frame x, y, z, which in turn is rotating with respect to the initial frame capital X, Y, Z. So this corresponding term as such 2 omega cross V x y z. In relative motion equation, this will be 2 omega cross V relative. Okay, both are the same thing. In terms of the relative motion analysis, which we will be dealing later, 2 omega cross the V relative vector. Now let us look into the relative motion interpretation of this equation. As I told you earlier, you have a moving frame xyz that is rotating with an instantaneous angular velocity omega with respect to the initial frame capital XYZ. Here RB in our equation it is R, and RA in our equation it is capital R, and RBA in our equation it is rho. Okay, so in most textbooks this corresponding format may be given, in which the corresponding base point A here represents the origin of the moving reference frame small xyz. Okay, and in most textbooks the thing is that instantaneous angular velocity of the moving reference frame small xyz is given by O. Okay, so as such, don't get confused, they are both the same thing. So I will write the equation here. Here we are representing this origin as VA and the point P as VB. So as such, I can write the same equation which we had derived earlier as VB is equal to VA vector plus VB with respect to a small xyz plus omega vector cross RB with respect to A. Similarly, the acceleration AB can be given as acceleration of point A plus AB with respect to A small xyz plus 2 omega cross VB with respect to A small xyz plus omega dot cross RB with respect to A plus omega vector cross RB with respect to A. Okay, both are one and the same thing. It is just two different ways of representing the equation. So I'll just write here the terms once again. So as such, VB or AB is actually V capital XYZ and A capital XYZ. Okay, VA vector comma A vector is actually R dot vector and R double dot vector. Then you have VB with respect to A small xyz and A B with respect to A small xyz. That is actually velocity with respect to small xyz and acceleration with respect to small xyz. Then RB with respect to A vector is actually the rho vector. So they are one and the same thing, it's just two different ways of representing the equation. To get a better understanding of the practical side, let us discuss certain problems or figures. Okay, first I will go into the planar motion. Now on the left hand side you can see a ride in an amusement park. The primary frame of reference is attached to this point A, which is rotating with an angular velocity omega AB. The secondary frame small xy is attached to the point B. Now the secondary frame of reference is actually undergoing a rotation with respect to the primary frame with an angular velocity omega AB. This corresponding disk attached to point B is actually rotating with an angular velocity omega dash. So in order to find the velocity and acceleration at the point C, you have to use the above equation because point C itself is in motion. Okay, the vector BC is not fixed. Vector BC itself is undergoing some angular velocity omega dash. So in order to find either the velocity or acceleration, you have to use the above equations. Okay, either in this format or in this format. Okay. Similarly on the right hand side, okay, you can see a system of rigid bars that are connected by pin joints. Okay, primary reference frame capital XYZ fixed at point O. The moving reference frame small xyz can be attached to the point A. Now small xyz is undergoing an angular velocity omega 0 with respect to the fixed frame capital xyz. The point B here, if you want to find the corresponding velocity and acceleration of point B, then remember one thing, that AB itself will be undergoing an angular velocity omega AB. So as such, if you want to find the corresponding acceleration and velocity of point B, we will have to use the equation as described in this lecture. To make things simple, let me tell you one thing. If there are two different angular velocities, okay, there are two different angular velocities. On the left hand side you can see omega AB and omega dash here, that do not pass to the same point. Okay, so you have omega AB with respect to this and omega B with omega dash with respect to point B. Okay, here you have omega 0 with respect to point O and omega AB with respect to point A. So in such cases we have to use the corresponding equation as per described in this lecture, where omega is not equal to omega bar. Let us come to the three-dimensional case. On the left hand side you can see the corresponding disk that is rotating with respect to an axis at point B, which in turn is rotating with respect to a point O. So as such, I can use the second equation here for solving this problem. Now the primary reference xyz here is attached to point O. Remember one thing, primary reference xyz does not rotate, it is fixed, and the secondary reference frame here is attached to point B, small x, small y, small z. Now since shaft here, okay, and this shaft here is undergoing an angular velocity omega 1 and omega 2 with respect to the x-axis and with respect to the x-axis and with respect to the y-axis, I can say that the corresponding moving reference frame is undergoing an instantaneous angular velocity omega 1 given by omega 1 plus omega 2, omega given by omega 1 plus omega 2. Now the question is to find the velocity and acceleration of point A at the rim of the disk. BA vector here is rotating with respect to the moving reference frame with an angular velocity p here. That means BA vector here is not fixed. So in order to find the velocity or acceleration of this point A here, we have to use the equations which we have derived in this lecture for determining these values. Okay, on the right hand side it is actually a robotic arm here. Okay, now I fix the corresponding primary reference frame capital X, capital Y, capital Z with respect to point O. Okay, and then the secondary reference frame small x, small y, small z with respect to point O2. Now you see you have the robotic arm undergoing angular velocity with respect to the vertical axis omega 1, then you have here the angular velocity omega 2, and as such you have also the angular velocity omega 3. All of these three are passing through the same point here. So as such I can say the moving reference frame small xyz is undergoing an angular velocity, an instantaneous angular velocity given by omega equals omega 1 plus omega 2 plus omega 3. Now suppose we want to find the velocity and acceleration of this point A here. Okay, this point A here. Now you have the corresponding O2A vector which is undergoing an angular velocity given by omega 4 plus omega 5. These two values does not pass point O1 but pass point O2 here. That means there are two different points of rotation here. And as such I can use the equation which we had derived in this lecture for determining the velocity and acceleration of point A. Velocity and acceleration of point A. Okay, so as such, in simple terms, if there are two different points around which the rigid body rotates, then we will have to use the equation where omega is not equal to omega bar. Okay, in the next class we shall be solving some problems related to this topic in which the xyz is not embedded within the rigid body. Okay, thank you all.